This video is going to be over the 2017 international practice exam, not just US, international, just the free response part. I don't know if I'll cover all the questions here, but go through some of them. As the test has changed this year, not everything is being covered, but so we'll skip a few things in here, but for the most part, we'll do a majority of the questions. So I'm going to just go to preview here. I've assigned it to you guys. Hopefully it opens here. So just a quick run through of some of these questions. First one's an acid-base question, which they're not going to have a lot of acid-base stuff, if at all, in there, but I think we can still do a little bit of this one. Dissociation of this weak acid, acetic acid. Again, here's your dissociation, making hydrogen ions and its conjugate base, the acetate ion. Remember, this would be a weak base, weak acid. Students first has to prepare 100 milliliters of 0.115 molar acetic acid from a 2 molar standard solution. So you've got this 2 molar standard solution of this weak acid. You can make 100 milliliters of this molarity. So this is a simple MV/MV problem. So this molarity times 100 milliliters equals this molarity times V. Divide and get they will tell you how much of this you need. You do that, you need about 5.75 milliliters of this is the answer there. So what that means is you would actually have to put about 94.25 milliliters of water with 5.75 milliliters of this to have this concentration at 100 milliliters. So simple MV/MV. Next part's a pretty common question. They say, describe the procedure the student should use to prepare 100 milliliters of this. So to make this solution that we did up here, so using the appropriate lab equipment from the list below, assume that the student uses the appropriate safety equipment. So here's the stuff they are giving you. One thing on here, a volumetric flask. I've shown you that before, but here's a volumetric flask. It has one marking on it. On the neck right here, so this is a 1,000 milliliter volumetric flask. It's got one marking. It's very, very precise to that one marking. So you have exactly 1,000 milliliters in that flask in this case. So here's the procedure that AP gives that you should do. Use the burette to deliver 5.75 milliliters. Okay, that's better than a graduated cylinder because it's more precise. Okay, so the burette is better. So you're going to put that much in the 100 milliliter volumetric flask. Again, you're putting it in this volumetric flask rather than a beaker because this is much more precise than the beaker is. And then add water. Remember, it's always water. Usually it's acid to water. So you could have said put some water in there first and add acid later, but since it's a weak acid, you're okay. Add distilled water from the wash bottle to the flask until you get to the 100 milliliter mark on the volumetric flask. So 2-point question, one for using the burette, one for using the volumetric flask. Next question here, make this fairly quick because there's not going to be much acid-base stuff this year, but using a pH probe, the student determines that the pH is of this 0.115 molar weak acid is 2.92. So remember, we can do 10 to the negative 2.92 to get concentration of H+. So if we go back up here, that gives us concentration of H+ or H0+, which would also be the same concentration as this. We know the initial concentration of that. So at equilibrium, we now know from the pH, we know these two things. We can do this minus those concentrations to give it this concentration at equilibrium, but get the Ka value from there. So as we show this, they did 10 to the negative 2.92. That's your concentration of H+. K expression, so this is 0.0012. This is 0.0012. This was initially 0.115 minus the 0.0012. Really not much change here. You probably could just leave it the way it is, but there's your Ka value. Next one, figure out the percent dissociation of ethanoic acid. So remember, we know what this was initially. We know what this is. So we can just divide how much this is divided by what that was initially. So the 0.0012 that they had figured out from there divided by the initial concentration, it's about 1% dissociation, hence it's a weak acid. We did a little bit of titration stuff earlier in the year, but a student titrates 10 10 milliliters of the 2 molar acetic acid with some NaOH. So now we have a strong base, weak acid reacting. So here's your titration curve. Your weak acid initially had a pH of about 2.5. As it's being titrated, the pH is going up because they're adding NaOH in there. This is how much NaOH they're adding, so that's why the pH is increasing, because you're adding a strong base. The only thing I'm going to tell you about this is right in here where the curve gets flat, up and down, is your equivalence point. That's when you have equal amounts of NaOH, equal moles, I should say, of NaOH with this. So however many moles this is, 0.01 liters times 2 moles per liter. At this point in time right here, you would have used the same number of moles of NaOH. So if we ever want to know this concentration of NaOH, we could do a little MVMV where we have this molarity and this volume of our acid equals our milliliters here, about 14 milliliters. So we could do MV on that side and figure out the concentration of the OH negative in that case. So look here. First of all, here's the reaction. Here's your weak acid. Strong base, all you include is OH negative. Weak acid, you include the whole thing because it does not dissociate very much. One-sided arrow in this case. H plus goes to the OH negative to make water and your conjugate base. They didn't do MVMV, but it would have been just as easy to do MVMV to get the concentration of OH negative. All right, that's all we're going to work on in that question. I'll do one more on this video. Question 2. A student investigates the reaction between hydrogen peroxide, and this is actually bleach. You don't have to know that, but sodium hypochlorite. Here's your net ionic equation. First thing, is the reaction represented above a redox reaction? So all you need to do is figure out, did any charges change from one side of the equation to the other? So just go through and look at your charges. If you can prove a charge change, it is redox. If no charges changed, it's not redox. So hydrogen's a +1 and a +1. This is the peroxide ion, so if your total hydrogen here is a +2, total oxygen here is a -2. That means each oxygen here must be a -1, and oxygen here is -2. So we know oxygen is being reduced, so this is a redox reaction. Oxygen is also going up in charge to a 0 over here. So there is a change in charge here, so it is redox. That's all you'd have to do to justify your answer. Next part of this gives a delta G and delta S. So entropy and Gibbs free energy we have not covered. It's Unit 8, so those will not be covered on the test. So we will skip that part, but we can do E through G here. Okay, so they're doing a little reaction. Student produces 40 milliliters of oxygen gas at a pressure of 0.988. Okay, so they're doing this reaction over here. Okay, dropping that into the sodium hypochlorite, collecting the gas over here over water. So remember, that means in this tube right here there is the gas collected, which in this case is oxygen gas. These are liquid and aqueous. And remember, whenever you collect a gas over water, there's also some water vapor in there, but not a whole lot. So you get 40 milliliters of oxygen in this container, in the udiometer. It's at 0.988 atmospheres. That's total pressure. So that includes the oxygen and the water vapor. And a temperature of 298 degrees Kelvin. Question E. Figure out the volume of 0.8 molar H2O2 that the student should add to excess NaOCl to produce 40 milliliters of oxygen at 0.988 atmospheres and 298 Kelvin. So it wants to know from our reaction up here, how much of this to produce 40 milliliters of oxygen gas. Well, it'd be nice to know moles of this. We can do our mole ratio to get over here and figure out how much of this had to be used. So to get our moles of oxygen, we're going to have to do a little PV/nRT. So we have to do PV/nRT. Remember, your milliliters has to be in liters, so that'd have to be 0.04 liters. Pressures in atmospheres, so that's good. Temperatures in Kelvin. R is 0.0821. So you can get your moles of oxygen, do our mole ratio, which is a 1-to-1 to get back to hydrogen peroxide, and it's 0.8 moles per liter to get from moles to liters. So look at that. So they PV/nRT'd, got this many moles of oxygen. The ratio is 1-to-1 between oxygen and hydrogen peroxide from the balanced equation. So that's your moles of H2O2 needed. To get from moles H2O2 to liters, we use molarity, 0.8 moles per liter. 2-point question, 1 point for doing PV and RT right and getting moles of O2, 1 point for doing stoichiometry correctly. Letter F here, student added the amount of H2O2 calculated in part E, which we just looked at, to XSNaOCl. However, instead of producing 40 milliliters of O2, the volume indicated in the diagram below is produced. So let's figure out what our volume is here in this case. So looking at that, based on the diagram, what volume of gas was produced, always make sure you do that to the correct number of sig figs as you're doing things. So if we look at this, notice our numbers are going from 30 to 40. This is 35, this is 36. So, 36.5, 36.4, but something with a decimal place, you can estimate that 1 digit beyond there as you're doing things. Assume that all the gas in the tube is O2, assuming that all the gas in the tube is O2, figure out the percent yield of O2. Well, we can take our actual amount of O2, 30, whatever we just said, 36.5 milliliters O2, divided by 40 milliliters, and get a percentage. It ends up being about 91%. And then, is the assumption that all the gas in the tube is O2 correct? Well, remember, they collected the gas over water vapor, so there would also be some water vapor gas in there. So no, that assumption is not correct. And then letter G on there. To account for the percent yield being less than 100%, the student claims that the reaction reached equilibrium before expected amount of O2 is produced. Considering your answer to this one above, do you agree or disagree with the student's claim? I would say no, since some of that is water vapor in there. The other thing is something else you don't know. This reaction has a very large K, which you would have figured out if we didn't skip a part in there because you don't know how to do that part. But has a very large K, so the reaction goes to completion. So you would think all of the H2O2 would produce O2. Not really a question you can answer at this point in time. We'll stop right there.